Hello, in this session we focus on the use of shortcuts and tricks in solving linear congruences. Linear congruences appear very often in problem solving under number theory, and there is always the need to arrive the answer as fast as possible. When you have a linear congruency of this form, the tendency is to look for the multiplicative inverse of the coefficient of x and then multiply it on both sides of the congruence with the aim of making x the subject. The process of finding the multiplicative inverse being long because we have to go through Euclidean algorithm, there is the need then to look for shortcuts that we can use to solve problems of this nature. The first thing, in order to use the shortcuts that I'm going to present, is the need to find the GCD of the coefficient of x, which in this case is 3, and the modulo, which in this case is 7. If the GCD divides the number immediately after the congruent sign, which is 4 in this case, then there is a solution. And when the GCD is 1, there is a solution unique in modulo 7 in this case. When it's not 1, then there are solutions corresponding to that GCD in the particular modulo that we're dealing with. So the shortcuts that I'm showing are particularly used when the GCD is 1. So in this case the GCD is 1, so it would apply. There are quite a good number of tricks that you can use in solving this linear congruence. The principle behind the tricks that I'm going to show is that once the GCD is 1, it is possible to cancel a common factor on both sides of the congruence, and that is how we can bypass the finding of the multiplicative inverse of the coefficient of x. You would have to know that an integer a is always congruent to itself in a particular modulo, and it will still be congruent to a multiple of the modulo. So if I'm dealing with modulo m, then a will be congruent to a and will still be congruent to a plus a multiple of that modulo m. So the k should be an integer. So that is the principle that we are going to be using for these shortcuts. I will start straight away by demonstrating the first trick that you can use in solving 3x is congruent to 4 mod 7. I can modify 3 or 4. It's either I modify the coefficient of x or I modify the number immediately to the right of the congruent sign, which is usually the remainder in the real sense. So I simply either add or subtract 7 on any of those numbers in order that I can be able to have a common factor on both sides which will cancel. As I said, the aim is to bypass the finding of the multiplicative inverse, which will take a longer time. So in this first trick, I'm going to subtract the modulo, because I've observed that if I subtract the modulo from the coefficient of x, I will get an integer that is able to cancel on both sides of the congruence. That is the trick. So this will be congruent to 4 mod 7, and we see now that negative 4x is congruent to 4 mod 7, and I can now divide both sides by negative 4. We are dealing with the world of integers, and so we cannot divide both sides by a number that will not cancel on both sides. That is the constraint we have in dealing with modular arithmetics or solving linear congruences generally. So this gives now x congruent to negative 1 mod 7. Now congruences have solutions only in the set of integers, and usually the solution is in the set of integers congruent in modulo 7 or the set of residues modulo 7. which usually has to be that x should be in the set of residues modulo 7, which range from 0 to 6, because normally a number in modulo 7 simply means the remainder when that number is divided by 7. And so the remainder when you divide something by 7 should either be between 0, it should be from 0 to 6 rather, and so the answer needs to be in the set of integers between 0 and 6. And so we have to modify the answer from -1 to a number in that set between 0 and 6 simply by adding the modulo. So I add 7. I can add 7 as many times as possible until I arrive this set, especially when you have a big negative number. So in this case, already adding 7 once, I can arrive that set. And so x is congruent to 6 mod 7. As I already said, 6 is the unique solution because the GCD of 3 and 7 is 1, and when the GCD is 1, we have a unique solution in modulo 7 in this case. So this is one trick that we can use. There is another possibility of solving. I instead take 3x congruent to 4 minus 7. I modify but the right hand side by subtracting again 7. Since the modulo is 7, it will give me a number that is still congruent to that 4 that was there in modulo 7. This now gives 3x congruent to -3 mod 7. And I can now divide both sides by 3 so that I have x congruent again to -1 mod 7, which gives, as already explained in the previous case, it gives 6 mod 7 as the unique solution in modulo 7. Another possibility would be to instead add, so I put again 3x congruent to 4 mod 7. I can instead add the modulo to the right hand side, or rather a multiple of the modulo, in such a way that the right hand side would contain a multiple of the coefficient of x, in this case 3. So if I put 4 plus 7, I have 11. 11 is not a multiple of 3. I add again 7, and that gives 18. So 3x is congruent to 18 in modulo 7. In this case now I divide again both sides by 3, and I have that x is congruent to 6 mod 7, again as before. One other possibility again is to find the multiplicative inverse of 3. In modulo 7 and then multiply on both sides. It has to do with doing so by inspection. So you find this multiplicative inverse by inspection, because again the aim is to solve the linear congruence as fast as possible. To do this, you take multiples of the modulo. So I'll verify 7 plus 1. The aim is to look for, I have to verify a multiple of the modulo that if I add 1 to it, would be able to cancel with 3. So a multiple of the modulo that if you add 1 to it, it will be a multiple of 3. That is the first thing to do. So 7 plus 1 is 8, and 8 is not a multiple of 3. I move to the next multiple of 7, which is 14. 14 plus 1 is a multiple of 3. So once I have that number that is a multiple of 3, and you can subtract 1 from it, and it will give a multiple of 7. So in this case it is 15. I divide 15 by the coefficient of x, and that gives me the multiplicative inverse I can use on both sides. So 15 divided by 3 gives 5. That means 5 is a multiplicative inverse of 3 in modulo 7. And so I multiply 5 on both sides of the congruence to have this. At the end now I have 15x is congruent to 20 mod 7, and 15 in mod 7 is 1, so it gives me x on the left hand side. X is congruent to 20 in modulo 7. Simply means what is the remainder when you divide 20 by 7, and the remainder is 6. So it still gives me 6 mod 7, the unique solution that we had using the other 3 shortcuts.